In this session, few previous problems from Pericyclic reactions were solved. This question has appeared from CSR December 2019 exam. The true statement for the following transformation is, so we have two reactant substrates and a product is given here, and this is cyclopenta, diene, and a malic anhydride under thermal condition gives this product. So for this reaction, we need to find the values of the enthalpy and entropy. For most of the chemical reactions, we would proceed from high energy to low energy state. So in this case, the change in enthalpy is equal to energy of products minus energy of reactant. As we know that the product's energy is always less than the reactant's energy. So that this value will become a negative value, and so enthalpy will be negative. And for finding the entropy, we need to know the number of product molecules minus number of reactant molecules. In this case, we have one product molecule and two reactant molecules. So the value will be uh, negative value. So the correct option for this question is both entropy and enthalpy are negative. So the other question, which was from CSR December 2019 exam, the intermediate A and the major product B in the following reaction is. This is the intermediate A, and this would be the final major product B. In this case, the given substrate is now treated with the methyl iodide. And first step is the formation of N-methylation. So we have lone pair of electrons. The same substrate is written here. The lone pair of electrons are used to displace this iodide. So first step is the formation of N-methyl intermediate. N-methylation happens, and after this N-methylated product is formed, this again was treated with potassium carbonate and DBU. DBU is a base, diazo bicyclo, and dicene. It's a hindered base. What this would do is it generates the anion here, as this anion is stable and this products are stick. The anion is generated here, and once this species is generated, it would be a suitable substrate for doing 3,2 sigmatrophic reaction. In this case, the number is given like this. This terminal sp2 carbon is given 3, 2, 1, and this is given 2 and 1. Now, in this case, the bond is formed between the carbons numbered 3 and 2. So the name is 3,2 sigmatrophic reaction. So the same substrate is written in this form here. So now we are making the bond between the carbons numbered 3 and 2. This is 3 and this is 2. And look at the electron rearrangement, and this negative charge will make a bond with this. Then this p electrons will move here, and this would become double bond, and this sigma electrons would move on to nitrogen, make it a neutral atom here. So again, in this case, the COMe group is arranged in a approximately equatorial position, and we have CH3 also in a equatorially down. This is equatorially down, this is equatorially up. So the product will be, this will be down, this will be up, and this option is now matches with the option 2. This N-methylation followed by enolate generation or anion generation, and that would be again going through 3,2 sigmatrophic rearrangement reaction gives this product. And this question was asked in GATE 2019 exam. The products found in the following reaction is, now this is a hexadiene 3,4 dimethyl hexadiene, or also you can take it as 1,5-dienes. If you start giving numbering to this terminal 1, 2, 3, 4, 5, 6. So this is a 1,5-diene with the substrates of this kind, like 1,5-dienes. You can do 3,3 sigmatrophic rearrangement reaction. Now you can write the substrate here like this, and as both the methyls are above the plane here, these two are arranged above the plane here. This is axially above and this is equatorially above. So this configuration is maintained here, And now the terminal carbons, the two terminal carbons are given the numbers 3, 3, then this takes 2, this takes 1, and 3, 2, 1. Then the bond will be formed between the carbons numbered 3 and 3, and bond is broken between the carbons numbered 1 and 1. These pi electrons through this carbon makes bond with this carbon, then this pi electrons would come here and makes a double bond, then this sigma electrons would come on here and make it double bond and would give this product. And if you observe the product, the new two double bonds formed are, one will be cis geometry, the other is trans geometry. So the given options, and the first option, both the new double bonds produced after 3,3 sigma-trophic reaction are trans double bonds. So this is not true, as we have produced one cis double bond and one trans double bond. Now in this case, both are cis double bonds, but this option, in this option, we have one trans double. This is trans double bond, and this is cis double bond. So the correct answer for this question is option C. And what is very important is writing the methyls on the same, both are on the same side, both the methyls are up. So it is written axially up, and this is equatorially up. And this was again asked in GATE 2019 exam. The number of following dienes that undergo Diel-Sutter reaction with methyl acrylate. The diene, the condition for the dienes to undergo Diel-Sutter reaction is they must be cis-side. So this is a cis-side double bond, and this is a trans-side double bond. In case of cis-side double bond, the two double bonds must be cis. And in case of trans-side double bond, if you look at about this sigma bond, these two double bonds are trans to each other. So this is a trans-side double bond. And with respect to this single bond, these two double bonds are cis to each other. So this is a cis-side double bond. The cis-side double bonds would easily undergo Diel-Sutter reaction. So in this case, we have a cis-side double bond, and we have cis-side double bond, and this is trans-side. This would not undergo Diel-Sutter reaction. Again, a cis-side, it will undergo Diel-Sutter reaction. Now this would become an example of trans-side double bonds, and again cis-side double bond and cis-side. So the only substrates which would not undergo Diel-Sutter reaction is this trans-side and one more trans-side. The other are, all the five would undergo Diel-Sutter reaction except this trans-side forum and this trans-side forum. So the number would be 5. And in addition to that, you must also be knowing the furan, pyrrole, and thiophene. These are the substrates for Diel-Sutter reaction, as all of them have the cis-side double bonds, but they would undergo the Diel-Sutter reaction at a different rate. With the highest rate you could expect from the furan. And this was asked in June 2019 exam. The major product formed in the following reaction is, this is the given substrate. The substrate is treated with lithium hexamethyl disilane. It's a hindered base, and trimethyl silyl chloride. It's an anion capturing reagent. Then heating the substrate. Now further it would be treated with the phenyl selenium chloride and H2O2. Now this is the lithium hexamethyl diacylyl amide, a hindered base. What this hindered base will do is it would abstract the acidic proton. This is the acidic proton and generates the inert. As the anion generated here will go here, makes a double bond, and O will become O minus. That O minus is captured by this trimethyl silyl chloride. Our silicon is more exophilic, so that O minus would bond onto silicon group with the chlorine, leaving us chloride. So silyl enol ether formation. This is what the enolate is captured with the silicon reagent. So trimethyl silyl enol ether is formed, and once this is formed, it would be a suitable substrate for doing 3,3 sigma trophic rearrangement reaction. And for doing 3,3 sigma trophic rearrangement reaction, we need to give the numbers the number 3 is given to terminal carbon. This is the terminal sp2 carbon. This also is a terminal sp2 carbon. Both the terminal sp2 carbons are given numbers 3. Then you can proceed towards 2, 1, then 3, 2, 1. And we need to make the bond between the carbon numbers 3 and 3 and break the bond between the atoms numbered 1 and 1. In this case, where is it shown is, so here it is shown, need to make the bond between the carbons number 3 and 3. So this pi electrons through this carbon will make a bond with this carbon. Then this pi electrons will come onto this sigma bond. It will become double bond. Then this bond would come onto here. This makes the double bond. This is what we will get after 3,3 sigma trophic reaction. Then when it is done, it is again treated with the phenyl selenium chloride. This phenyl selenium chloride and this O minus would come on to this single bond, will become double bond. Then this pi electrons through this oxygen would make a bond with this carbon. Then this pi electrons through this carbon makes bonding with the selenium, and this chlorine would leave us chloride. And once this is formed, it is now oxidized with H2O2. The selenium oxide is formed that would get rearranged to this form by abstracting this proton, and this bond electrons will come onto here, makes it double bond, and this sigma electrons would come onto silicon and make it a neutral species. That's how this product is formed. It matches with the option 1. Now here in this case, the co-rearrangement, the mechanism for co-rearrangement is shown here. This is the example for 3,3 sigma trophic rearrangement reaction, as we have a 1,5 diene system. A 1,5 diene system. This is called a 1,5 diene system is there. The 1,5 diene system, we can perform 3,3 sigma trophic rearrangement reaction, and the terminal sp2 carbons are given numbers 3, 3. Then again this makes 3, 2, 1. Again from here 3, 2, 1. Now a bond is being formed between the carbon number 3 and 3, and the bond which is broken is the carbons number 1 and 3 with the rearrangement of pi and sigma electrons. This pi electrons through this carbon make a bond with this. Then this pi electrons will come here, make it double bond. Then this sigma bond would come on to this bond, makes it double bond. So thus we will get this product. Only thing is we need to be knowing the bulky group must be present always in the equatorial position. In this case, the phenyl is bulky than the methyl, so it will first be in equatorial position. So in this case, this is not the preferred intermediate because the bulky group is in axial position. So this is disfavored over this. So the product we will get is this. So this is the example of doing 3,3 sigma trophic rearrangement reaction. And here few examples are shown for Claisen rearrangement, Johnson-Claisen rearrangement, and Eschen-Moser Claisen rearrangement, Ireland Claisen rearrangement. For Claisen rearrangement, we need to have a allylic alcohol that will be treated with ethyl vinyl ether in presence of Lewis acid mercurous ion. So what is formed is ethyl vinyl, allyl vinyl ether is formed. This is allyl vinyl ether is formed. This allyl vinyl ether is a suitable substrate for 3,3 sigma trophic rearrangement reaction because this is an example of 1,5 diene. If you start numbering from this 1, 2, 3, 4, 5, 6, so it's a 1,5 diene. And for doing 3,3 sigma trophic reaction, we need to give the terminal sp2 carbons 3, 3, then proceed to 1, 2, 1. Then make the bond between the carbons numbered 3 and 3 and break the bond between the atoms numbered 1 and 2. Then you will get this molecule. So this is an example of Claisen rearrangement, same as 3,3 sigma trophic rearrangement reaction, but with only difference is we have a oxygen atom in the main chain. So other variation of a Claisen rearrangement is Johnson-Claisen rearrangement. In case of Johnson-Claisen rearrangement, we'll start with allylic alcohol, and that would be treated with trimethyl orthoacetate, trimethyl orthoacetate, or it can be trialkyl orthoacetate. So when you treat this with, this is the intermediate formed with all the rearrangements. This lone pair of electrons present on oxygen would displace one of the ethoxide. Then the lone pair of electrons present in one other methoxy would displace one more methoxy. Then it would again get rearranged to this form. It would be a suitable substrate for doing 3,3 sigma trophic reactions. Then you will get this after doing the 3,3 sigma trophic rearrangement reaction. The other variation of the Claisen rearrangement is Eschen-Moser Claisen rearrangement. In this case, allylic alcohol is treated with N dimethyl acetamide, dimethyl acetal is treated with in presence of acid will get rearranged to a suitable form of 1,5-diene system, or it can be a substrate for 3,3 sigmatrophic rearrangement reaction. We do the 3,3 sigmatrophic rearrangement reaction. This is the product we'll get. And finally, this iron Claisen rearrangement. In this case, allylic alcohol is acetylated with acetic anhydride in presence of a 11 base. Then acetylation is done. Then that would be silylated using a base that can be converted to silyl enol ether. Then that would be get rearranged into this form by 3,3 sigmatrophic rearrangement reaction. So the next problem is from CSR June 20 on an exam. The major product from the following reaction is. So this is the substrate given, and this is the under thermal conditions. So this would become an example of electrocyclic ring closing reaction. For electrocyclic ring closing reactions, we need to be knowing these 4 sets of rules for doing electrocyclic ring closing or opening. So 4n means 4n number of electrons, pi electrons, 4n thermal, conrotatively ring can be closed or opened. A 4n system under photochemical condition, this rotatively it can be opened or it can be closed. A 4n plus 2 system under thermal condition, it should be this rotatively ring can be closed or opened. A 4n plus 2 system under photochemical conditions can be conrotatory. Through conrotation, we can either close or open the ring. So in this example, if you consider all the 4 pi bonds, means 8 electrons. 8 electron system is a 4n system. 8 electron system is a 4. If you start giving numbers to n is equal to 0, 1, 2, 3, 4, then you will get 4n is what? So 4n, if you make n is equal to 2, it will become 8 electron system. So 8 electron system is a 4n system. If you give n is equal to 1, it will become 6 electron system. So 6 electron system is a 4n plus 2 system. So if you give n is equal to 2, here in this case, if you give n is equal to 2, it will become 10 electron system. 10 electron system also is an example of 4n plus 2 system. Now, if you consider all the pi electrons here, it will be 8 electrons. So 8 electron system is a 4n system. A 4n system, if you consider all the pi electrons or all the 4 pi bonds under thermal conditions. So 8 electrons means 4n system under thermal. We need to close it conrotatively. So we need to close conrotatively. So for doing the conrotative ring closing, we must now concentrate on the substituents of the terminal carbon. So this is the terminal sp2 carbon. The substituents here as one is hydrogen here, the other is nitrogen here. And for this terminal sp2 carbon, the one substituent is nitrogen, the other substituent is hydrogen. That is shown here. This is terminal carbon. This also is terminal carbon. These two are the substituents with respect to this terminal sp2 carbon, and these two are the substituent with respect to this terminal carbon. So as we have considered the 4 pi bonds or 8 electron system, we need to close this ring through a conrotation fashion. If we do a conrotation, closing the ring through conrotation, then how do we close it? So we need to rotate the terminal sp2 carbons or the two substituents which are attached to the terminal carbon in a clockwise direction like this, and this also be in a clockwise direction. Both must be rotated in the clockwise rotation. Then this will go up, this will come down. So this is what is produced after closing this system by considering all the 8 electrons or all the 4 pi bonds. It will produce a 2 fused ring system. In this case, a 3-membered ring and a 6-membered ring is fused in a trans form. So when these 2 hydrogens are trans, then this is said to be transfused. When these 2 hydrogens are cis, or the substituents of that carbons are cis, then that is said to be cis-fused. So the smaller ring size, like 3-membered ring and 4-membered ring, they cannot fuse in a trans fashion. So this is less likely to form. And when only 3 pi bonds are considered here, without considering this, then we are now having 6 electrons. We are now having 6 electrons. 6 electron system is a 4n plus 2 system. 4n plus 2 under thermal disrotation. So this must be closed in a disrotation fashion. Disrotation is if we rotate the a terminal sp2 carbon or the terminal sp2, the substituents of the terminal sp2 carbons. One takes the clockwise, then this must be rotated anti-clockwise. These two substituents of this terminal carbon must be rotated anti-clockwise. So this hydrogen will come up. This hydrogen will come up as this is doing a clockwise rotation and this is doing anti-clockwise rotation. So we will get the two systems fused like this, and with the moment of with the rearrangement of pi electron system. So this pi electrons through this carbon makes bond with this. Then this pi electrons will move here, and this pi electrons will move here. That is what the system is formed. And these two hydrogens will now become cis to each other because we are doing now 4 plus 2 thermal disrotation. Disrotation is nothing but the rotating the substituents of the terminal carbons in different directions. So if you rotate this in a clockwise, you must rotate these two in a anti-clockwise fashion. You end up getting the product, a bicyclic fuel system with the two hydrogens cis to each other. So the answer for this question is the first one. So why we did not go is we cannot fuse a small membered ring in a trans fashion. So though it is allowed, with these asymmetry rules, we cannot go to this because a transfused system is formed with a small cyclic ring that's not stable. So the answer for this is now 1. That's all is about these reactions from pericyclic reactions.